we have Oscar Henriksson, who is going to discuss about dynamics of first-order phase transition in holographic theory.
Okay, thank you. So yeah, thanks to the organizers for letting me speak and for organizing. It's been very nice so far. So I'm going to ride the wave of David Matteus's talk earlier here. So he did all the kind of motivation for me, which is very nice. So I can be quick here in the beginning. So I'll talk about first-order phase transitions, and as David mentioned, they are very interesting for various reasons. For example, in cosmology, but also in every area of physics. And the dynamics are very complicated, even at weak coupling. And that's where holographic duality comes in and can do cool stuff, hopefully. So brief outline. I'll first quickly introduce kind of a neat, simple holographic model that I'll be using throughout to study phase transitions, sort of a toy model. And then I'll talk a little bit about bubble nucleation and how to do some stuff about that in holography very quickly. And then I'll focus mostly on point 3 here, which is when bubble nucleation is suppressed and you approach what's called the spinodal point. And all this is based on work, work from a few years ago about bubble nucleation with these very nice people, and more recent work about this spinodal stuff with these very nice people. Okay. So first of all, what I'll be using is this very simple holographic model, which is as simple as you can make it almost. It's just a scalar field and gravity. So this field phi is dual to some order parameter psi, and I'm going to choose its mass such that I can use this what's known as alternate quantization. Neumann instead of Dirichlet boundary conditions. And then I'll use even more complicated boundary conditions, because I'll do these kind of multitrace deformations, which you can do when you use this alternate quantization. So I'll basically deform my CFT by simple powers of this operator, and this is implemented in holography by some more complicated boundary conditions on this phi field. So this is very nice because it gives me these parameters here that I can use as knobs to just get what I want. And what I want is phase transitions. So we don't have to go into this figure in detail, but the point is that there are first order lines and there are second order endpoints, and there are just crossover regions. So you can kind of tune these parameters G, F, etc. to get what you want. And it's a very simple setup. Okay. So David already talked about bubble nucleation in first order transitions. So the picture is that you have your order parameter, if you call it that. There is some region of temperature or other parameters where you have this phase coexistence. So you have several solutions, several phases that coexist. In an effective potential point of view, you have several minima here, and at some point you cool down, for example, and at some point here the system wants to get to this other phase, but there is still a barrier, so you have to either tunnel through it using quantum or over it using thermal fluctuations. Okay, so this leads to bubbles, and you can compute stuff using this Callan-Coleman or Linde formulations. So I'll be very brief, but okay, you can find the critical bubble solutions from some kind of effective action, and the action of these bubbles is related to the nucleation rate. Okay, so very quickly I'll talk about this older work where we studied this in holography using this multitrace model. By the way, this model here we used 5 gravity dimensions, but you can later I'll work in 4. And we compute this. We study bubble nucleation by computing the field theory effective action for psi. Okay, so one way to study this would be to just try to find the gravity dual of a bubble solution and compute its action, but this requires PDEs and it's annoying. No one likes PDEs. So you can instead compute this nice effective action just by, in a derivative expansion, just by solving homogeneous equations. So you compute this V here, the effective potential, and this kinetic term through homogeneous solutions and fluctuations around them. And then you can get bubble solutions, everything is ODEs, it's easy peasy, and you can get all the nucleation rates and stuff that you want for these gravitational wave computations, for example. Okay, so that's all I was going to say about that. Now I want to go on to another related topic, which is what if bubble nucleation is suppressed, okay? So I think it was mentioned in David's talk also that if fluctuations are suppressed, which they are at large n, in particular, then bubble nucleation will not, it will be suppressed by some factors of n or some powers of n. And then you will supercool, you can supercool a lot before you complete the transition. And you can get close to this turning point here, which is this funny thing called the spinodal point. Okay? And then you might ask, what happens then? So one thing so these spinodal points are interesting, and because they are similar in some ways to critical points of second order transitions. Okay? So very naively, I mean, if this, in a second order transition, the derivative also, on a curve like this, the derivative of this curve also goes to infinity. You don't have this S curve where it turns back, but the derivative goes to infinity, and that's related to some susceptibility blowing up. And that happens also for spinodal points. So they have some things in common, some kind of their scaling behavior that happens next to them. And what's nice is that there are experiments, condensed matter experiments, that claim to see these effects, where they can kind of get super cool the system and get very close to the spinodal, and they claim to see signs of this scaling. Okay, so yeah, there is some various materials that you can do this on. So a bit more quantitatively, you have this sort of typical scaling relations, or with various powers, just like in second order transitions. And what I'll focus on is this thing called critical slowing down, which means that when you try to cool down towards this point, be it a spinodal point or a second order point, the relaxation time diverges, and the system, no matter how slowly you try to cool down, the system kind of cannot keep up. Like the system, you will be thrown out of, like this kind of quasi-equilibrium approach will not hold. This adiabatic approach will not work. So at some point you will be thrown out of equilibrium. Out of equilibrium. So if you're familiar with Kibble-Zurek, this analysis is a little similar to that. So I assume I'm cooling linearly in time near this either critical or spinodal point. So what I'm saying here works for both. So I have some factor here, some time scale that determines how fast I'm cooling. I define this, what I might call freeze-out time or something else, as the time when psi, the order parameter, departs by some amount from its equilibrium value. Okay, and if I then take the derivative of this, how fast psi changes in time, and compare it to the decay rate, or the inverse of the relaxation time, I get these scaling relationships. Okay, so it's a little bit similar, but also different from Kibble-Zurek. So I can come back to that later. But the point is that this is very simple. And in this holographic toy models that I introduced earlier, we can compute all these exponents. And moreover, we can do this numerical simulation, like actually cooling down the system and seeing what happens. Okay, so for this case, I'll go to the probe limit. So this scalar is a probe field, so it's even easier. than before. And I'll tune these. I make these multi-trace couplings that I talked about earlier time dependent, which roughly you can think of as I'm just cooling the system down towards the spinodal point. Okay, and we're doing some kind of real-time simulation and studying this scaling behavior. And since I'll just jump quickly to the results, and we just find the point is that we just find good agreement. Okay, so we find these scaling exponents that I talked about earlier for first-order transitions, so close to the spinodal point. The dotted lines here are simulations, and the straight lines are these theoretical exponents. And for second order, we can also do second order transitions, and we see the same thing very nicely. And we can also do some variations of this. For example, if it's a strong crossover, so it's not a sharp phase transition, but you're very close to a second order point, you can see signs still of this scaling behavior. Okay, so you don't have to have a sharp phase transition to see the scaling behavior. And also another funny thing is if you have a first order transition, but you're close to the second order critical point, the sort of end point of your first order line, you can see traces of both exponents. So both spinodal exponents and second order exponents. Okay, so it's kind of fun. You can kind of see traces of all of them. It's maybe not super clear here, but you have two different slopes here, and you see that some curves at least follow both of them to some extent. Okay, I guess I went very quickly. So yeah, okay, I have time to actually read the summary. So we talked about first order phase transitions, why they're important, and how you can treat this bubble nucleation in holography. So David talked about what happens when the bubble expands. I talked about the actual nucleation event, looking at that. And then when nucleation is suppressed, you can approach this spinodal point, and you see various critical phenomena. The system gets thrown out of equilibrium in some sense. And you see the scaling. We had this simple holographic model where we can easily look at all these stuff. And as usual, there's much left to do. For one thing, we assumed homogeneous fields in space here. So one nice generalization is to add spatial, allow the field to vary in space. And then you could, do various things. You could do Kibble-Zurek, which has been done by Julian, which I think is here somewhere, and others in holography. But you can do some variation of that, or real-time simulations of nucleation, similar to what David has been doing, but easier, because you don't, in this probe model, you don't have to do gravity, dynamical gravity. Okay, I think that's all I had to say. Thanks.
Questions?
Thanks. So when a bubble is nucleated, I might expect it to be small, and then do you run into any issues with the convergence of the derivative expansion or anything like that?
Yeah, that's a good question. In general, you have to worry about that. Yeah. So there are cases where it doesn't work. In the cases we looked at, we tried to compute at least a subset of the four derivative terms, and then evaluated them on our solution and saw that they were small. So we took that as it seems to work. More recently, in some unpublished work, we have tried to actually find the solution, the bubble solution on the gravity side, so by solving PDEs, and comparing it to the result of this effective action approach with the derivative expansion. And they seem to agree very nicely. So it seems to work, but you have to be a bit careful, I agree. Yeah.
Thanks.
So do you see any room for non-mean field critical exponents in these studies?
Probably not. I'm not sure. I mean, these multi-trace deformations kind of give you exponents that look a bit funny at first, but I think
But then they're just twice the single trace ones.
They're
no longer funny.
Yeah, exactly. They are not that funny when you think a bit more about it. So yeah, I think I'm not sure. I don't know.
Thanks.
Yeah, sorry.
Any more questions? If not, so thank you.
Thank you.